into machine learning and information ethics. And in this talk that I'm going to present to you, and I'm very grateful to Brandon who agreed to comment on it, is meant to start a kind of dialogue, a kind of conversation, I hope, with some of you, philosophers, computer scientists, policy researchers, legal scholars. I think philosophy of science should be in that mix, and I think it has something important to contribute. So this is in no way a finished product, it's an invitation. The title of this talk is Fairness in Machine Learning, a Measurement Theory Perspective, and that's because I'm a philosopher of measurement. Philosophy of measurement has really picked up in the last few years. These are some of the books. Most of these have just come out in the last 3 or 4 years. So you see, it's hard to see, but some of these are about measurement in economics, some about physics, some about well-being, psychology, medicine. And there are articles in these edited volumes about measurement in earth sciences, in climate science. Philosophers are engaged in this interdisciplinary subfield of philosophy of measurement, are interested both in the epistemology of measurement and in the ethics and how they interact. So on the epistemology side, we ask things like, what is measurement? Why do we trust measurement to give us evidence about the world? Why do we trust measurement to test theories? What's the relationship between, say, measurement and calculation, measurement and prediction, measurement and observation? And also questions about the kind of conceptual foundations of measurement. What is a quantity? What does it mean to say that a measuring instrument is accurate? How can we justify inferences about precision and error? How can we even know what the error is if we can't tell what the true value is? But also on the ethical side, how does the standardization of measurement affect different populations? Who benefits and who gets harmed by the way we define our measurement concepts? And that has a lot to do with the sociology and history of measurement. So my overarching question today is, what insights can the philosophy of measurement offer the study of fairness in machine learning? There's a way to talk about measurement in machine learning that's limited just to the collection of the data, the collection of the features and the labels in the training data set. Today I want to do something different. I want to talk about measurement in a broader sense. I want to start by making an analogy between machine learning algorithms and measuring instruments. What would happen if we start thinking about not just the data collection as measurement, but as the machine learning algorithm itself as a kind of measuring instrument? Can we gain interesting insights about fairness by doing that? So I'm going to try to set up an analogy. Then I'm going to talk about two assumptions of what I call static fairness criteria, the kind of conditional probability fairness criteria that many of you have already talked about. And I'm going to try to use the analogy with measuring instruments to see what happens when these assumptions fail. First, I'm going to distinguish between two kinds of accuracy in machine learning that I call instance accuracy and process accuracy. And this will, I think, directly relate to some of your talks, especially to Tina's talk, who's really done my job much easier, because a lot of what I'm going to say is kind of trying to, in a way, is going to justify many of her claims just from a different kind of independent direction. And then I'm going to introduce quickly a notion that I call definitional fairness that is relevant when the other assumption fails. And I'm going to summarize this talk by giving 4 principles for thinking about machine learning in terms of measuring instruments. Okay, so let's start with something simple, like a caliper. A caliper is an instrument that measures length, or in this case, diameter. You place an object between the jaws, and you read out the indication of the instrument. Now, if you're a metrologist, metrology is the science of reliable measurement. Metrologists are the people who work at the standardization bureaus. And you really want to know how accurate this instrument is. How accurate does it measure diameter? What you do is you construct an idealized model of this instrument. You conceptually divide or analyze this machine into modules. Up here is the diameter, and down here is the indication, the thing that you end up seeing in that little window. But intervening on the relationship between the diameter and the indication are different modules. So for example, the workpiece, what you're trying to, whose length you're trying to measure, the contact between the workpiece and the jaws themselves, the scale, and the readout. And each of these conceptual modules has various parameters associated with it, such as the temperature of the workpiece, the roughness of the contact between the workpiece and the jaws, the resolution of the readout, and so on. So, how can you tell how accurate this is? Well, what you need to do is, if you're a metrologist, is to specify functional relations, equations among these various variables, and try to see which values of the diameter variable best predict your indications. What you have to construct, in other words, is what metrologists call a calibration function. Calibration function takes the first parameter there is the indication, the number you see when you look through that readout little window. But it also takes all these influence quantities into account, such as the roughness of the contact, temperature of the workpiece, and so on. And that function transforms these input variables into an outcome, an estimate of the length of the object. Now, a few things to note. First, a calibration function is a model-based prediction about the behavior of the measuring system. How we arrive at this is by solving a bunch of equations. So this is a prediction about how the caliper will behave, what indication it will produce when interacting with certain kinds of objects. A direct consequence is that a measurement outcome is a model-based predictor, right? It's simply that O over there. It's a predictor variable that predicts the instrument indications under some idealized theoretical and statistical assumptions about how the instrument behaves. And this is already different than kind of the naive way of thinking about measurement outcomes as simply being read off the instrument, read off the world through the instrument. Measuring instruments are not these kind of transparent, flawless vehicles of observation. They are, measurement is very much model-laden. Okay, so measurement outcome is model-based predictor. Now, what does that tell us about accuracy? The accuracy of measurement is the accuracy of a model. It's the predictive accuracy of the idealized model of the measurement process. To be more precise, measurement accuracy is the predictability of the distance between the real measurement process and some ideal representation of the measurement process. If we know the degree to which we know that difference between the ideal and real is our measurement accuracy. Here's a more complex example, but the same underlying idea. This is NIST F1, one of two of the US's primary frequency standards. There are about a dozen clocks like this in the world. It's an atomic clock, and it's a primary standard, which means that it's responsible, along with about a dozen others, for tuning the frequency of almost all the clocks in the world. So all of your computers and cell phones, they all get calibrated to what's called UTC, Universal Coordinated Time. And Universal Coordinated Time is made of an ensemble of atomic clocks that are tuned against these dozens or so machines. about the size of a fridge. But in there somewhere are cesium atoms, and the definition of 1 second is the frequency associated with a transition between two states of a cesium atom. The definition, though, is an ideal definition, an idealized definition. The cesium atom has to be kind of hovering there without interacting with anything in flat space-time, no magnetic fields, no temperature, nothing. But of course, those conditions don't exist. So to know how accurate this machine is, metrologists model it. They have a long list of assumptions about how different features of the environment affect this particular machine and make it slightly different than the ideal. It looks like this. This is called an uncertainty budget. Each row in this table is one influence variable, one way in which some external factor makes the clock tick at a slightly different rate than the ideal. And each of these, so for example, the first one has to do with the effect of gravity, the second one with the effect of magnetic field, the third with temperature, the fourth with collisions between atoms, and so on. And each of these is associated with some offset, some difference between the ideal and the real, and that offset itself is associated with some uncertainty, because we're not exactly sure just how much, say, magnetic fields affect the frequency of this clock. The accuracy of this clock is simply the sum total, or the quadratic sum to be really exact, of all these individual uncertainties. So it's a total uncertainty about the difference between the ideal and the real measurement process. Okay, now that I've given you all this, why does it all matter? Well, let's see if we can set up a kind of an analogy between measurement and machine learning, and see if we can learn something new about, potentially about machine learning. So on the one hand, we have a measuring instrument. On the other, we have a machine learning algorithm. Well, we can say the measuring instrument interacts with some object, right? Some disk that has a diameter or a cesium atom. A machine learning algorithm also interacts in a slightly more metaphorical way with some object, say a person, by collecting data about that person. So the data generation process is kind of a mediated kind of interaction between the algorithm and some object in the world. A measuring instrument produces indications, the ticks of the clock, the number you see in the little window on the caliper. Well, a machine learning algorithm also produces something we can say is analogous to an indication that those are the predictions, say scores, probabilities, classifiers. I'll talk about scores in this table, but you can generalize to other output variables. Now, in the case of measurement, indications are used to infer measurement outcomes. And such is also the case with machine learning algorithms. Scores are used to infer values of the target variable. Now notice that this is a different direction from the way we usually talk about inference in machine learning. Right? Usually when we talk about inference in machine learning, we talk about the inference from features to the prediction. I think it's interesting and possibly just as useful for the sake of talking about fairness in machine learning to talk about the opposite kind of inference, from the scores we get back to some feature of the world. And I think that goes back exactly to Tina's emphasis on tasks, on defining tasks. How do we make that inference back from the prediction to the feature of the world that we're interested in? Well, in the case of measurement, we use a model. There's an idealized model of the measurement process. But we can say something similar about machine learning too. We can say that the inferences from scores to target variables is underwritten first by the machine learning model itself, say by the fact that we've minimized loss, and therefore the weights in our machine learning model are optimized for making that inference in the most accurate way possible. But that's not enough. We also need to talk about other things, such as We need to assume certain things about how the data itself was generated. And we need to make assumptions about the relationship between the features and and the target variable, not just in the training set, but also in whatever population or case that we're extrapolating about. And here's, I think, the most interesting bit of the analogy that falls out of this. If we take this analogy as potentially useful, then how do we understand accuracy? In the case of measurement, measurement is accurate relative to some idealized measurement process. Remember that the predictability of the difference between the ideal and real measurement process. Can we say the same thing about the accuracy of a machine learning algorithm? Can we say that a machine learning algorithm is accurate relative to some idealized use case? Now we're going to talk about the process by which the machine learning algorithm interacts with the world, the population, including the decision makers, the use pattern, and the effects of the decisions made in response to the machine learning algorithm. And we can ask, well, how predictable is the relationship between the ideal use case, the use case that we'd like to realize by using this algorithm, and the one we actually realize? Can we make that relation more predictable such that we can approximate the ideal use case with the real one? This is a very different way of talking about accuracy than the way we usually talk about accuracy in machine learning, right? When we talk about the predictor, the probability that the predictor will equal the value of the target variable. And I'll come back to that. But first, I'm going to take a step back and try to explain why I think any of this has to do with fairness. Right? Why would any of this have even relate to fairness? Well, we're all familiar, given everyone's talks, with what I call static fairness criteria. These are fairness criteria that take some sort of equality between groups to constitute fairness. Groups are equal with respect to a benefit or harm, and how you conceptualize that benefit or harm gives you different kinds of fairness criteria. So, for example, demographic parity equalizes the fraction of group members that receive a benefit or harm, equalized odds, equalize the error rates, so positive, negative, false positive, false negatives, and so on. Now, the reason I call these criteria static is that simply that they don't have any time variable in them, right? So you have conditional probabilities on one hand, conditional probability on the other, and an equal sign. They don't suppose anything about the evolution of these probabilities. And that's not necessarily bad, but it does mean that there are certain things that these fairness criteria can be expected to do, and some other questions that we probably can't expect these fairness criteria to answer. A common way of implementing a fairness criterion is to set the decision threshold just right so that the right sort of conditional probabilities are equal. But notice that this kind of common implementation of a static fairness criterion presupposes two things. First, it presupposes what I call the directionality assumption, that once you've set the decision threshold, the fairness is just fixed, right? Fairness doesn't loop back and then affect your accuracy. So error rates are the independent variable, and the fairness is the dependent variable. You fix them once, and that's it, you go home. Of course, given almost all of your talks, we know that's false, right? But it's not always false. There are cases in which we don't expect this kind of loop to happen, but there are cases in which we're pretty sure that there is a loop. And I'll talk about this in a moment. But there's another assumption, which I think is even more pervasive than even just talking about fairness criteria, I think it's kind of a very pervasive assumption in machine learning, which is the accurate example assumption. When we talk about accuracy in machine learning, we assume that there is access to some independent, accurate source of knowledge about the values of the target variable, and that is how we get our labels. But that also fails in some cases, interesting cases of machine learning. And I think there, the analogy with measurement is even more important. So we'll start with this one. We'll start in cases where the directionality assumption fails, and then I'll go back and talk about cases where the accurate example assumption fails. All right. So we all know about feedback loops, right? The directionality assumption is violated when fairness and accuracy co-evolve. The unfairness of the algorithm creates a social process, decision-making process such that the error rates of that algorithm are going to change in the next step. Duncan talked about predictive policing and some of the others as well. So sending patrol officers to a given area increases the probability that there'll be arrests in those areas, and that leads to biased prediction. Now, Momin, in his talk, already mentioned this wonderful book by Ian Hacking, The Social Construction of What. I'm putting it here just to remind everyone, this kind of feedback loop is nothing special to machine learning. It happens all the time whenever you try to classify people. Hacking talks about what he calls interactive kinds. So kinds of people, categories that interact with the people being classified. So for example, retarded children is one of his examples where you classify certain children as retarded. Their parents and caregivers rebel against the segregation of the kids to a different school. That feeds back into advocacy groups, lobbying groups. It goes back to change the societal values. The definition changes, the policy changes. Now we're talking about special needs, and then there's integration, then there's yet another iteration. Today we talk about intellectual disability, which is quite different from the category of retarded children. And this kind of looping between the class and the classified is very common when it comes to people. Right? We don't usually think it happens with electrons and quarks, but people are special that way. They do interact with being classified. So, what can we learn from this kind of broader analogy? Is there something more general to say here about how we may either escape the loop, or if we can't escape it, somehow harness it to increase fairness rather than to have kind of fairness run away from us? Can the analogy with measurement help us think about this interaction between accuracy and fairness? I think it can. Again, recall, measurement accuracy is evaluated as the predictability of a distance between an ideal and real measurement process. Instance accuracy, the normal way of thinking about accuracy in machine learning, has to do with the probability that the prediction will be equal to the value of the target variable. But what if we talk about process accuracy? Now we're talking about a different kind of probability. I don't know how to exactly formalize it, but here's how I think about it. I think about it as the probability that the system composed of the algorithm and the population will, after multiple iterations, will approximate what I call an ideal use case within some margin epsilon. So there's an ideal use case we want to affect. We're thinking of our machine learning algorithm not just as a predictor, but also as an intervention in society. Again, very much along Tina's talk. line. And we're trying to design the right kind of machine learning tool that will give us the right intervention. What's an ideal use case? Well, an ideal use case is a scenario in which both the instance accuracy, so we still care about this. We don't want to throw this kind of accuracy away. But what we want is something more than that. We want to create a scenario in which both the instance accuracy of the algorithm and the fairness of the distribution of harms and benefits in our population, by whatever criterion of fairness we adopt, reaches an optimal equilibrium and hopefully reaches that optimal equilibrium relatively quickly so that we don't have to wait a century before it happens. So this is a comparative notion. An ideal use case is a comparative, a relational notion that compares different scenarios. How do we actually improve process accuracy is, I think, a really interesting challenge for machine learning. It definitely involves modeling not just the data, but also the social dynamics that surrounds the use of the instrument, of the machine learning algorithm. There are, I think, examples out there of people who are already thinking in this way. Specifically, here's an example from Danielle Einstein and her colleagues at the University of Utah, who are modeling predpol, exactly Duncan's example. Here, this is a predictive policing tool where by itself, so before they introduce any modification, they just let it run 300 times for a year, and they look at the distribution of the relative deployment of police to these two top regions, the regions of most crime, the highest crime rates in Oakland, California, and they see that although the true crime rate by hypothesis is here, there's kind of there's first of all a big spread, and there's also a runaway effect, a feedback effect that sends too many police to area top 1. What they do is they model the feedback itself. They model the social process of sending police, increasing arrest rate, feeding back the updated features to the model, and then they introduce an intervention on the data that, according to the model, should counteract that feedback effect. And this is the result. There's still a spread, but the spread is around the true rate, and the runaway effect seems to be gone. Now, I'm not saying that this solves everything, right? There's still lots of problems. This is not kind of the end point of our attempts to improve fairness. All I'm saying is this is an interesting example of the kind of work that that takes seriously the idea of process accuracy and its relation to fairness. And I'm trying to give it a kind of foundation, an epistemological foundation. What about the other assumption? And this part will be very brief. The accurate example assumption, remember, is simply the assumption that we have some reliable source to give us our labels. Sure, sometimes we do. Often we do. We definitely, if we wait long enough, we know how many people will have skin cancer, how many people will be arrested, and so on. There are problems there too. But notice that this assumption is completely unacceptable for me. If you try to measure something by assuming that you already have an accurate way of measuring it, measurement will just never start. Right? The whole point of measuring is to find out something you don't yet know about, or at least find out what the value of a variable is more accurately than ever before. How can you find the next decimal digit of constant, say, if you don't already know it, where do measurement standards come from? And the answer, the short answer, and this is a very big topic in philosophy of measurement, is that measurement quantities become standardized through an iterative, gradual process of mutual refinement, in which the theoretical concept of the unit and the instruments you use to measure that quantity slowly, in a kind of slow dance, become aligned, and that's called coordination. In that process of coordination of the theoretical concept of the quantity and the instruments used to measure it, the concept becomes sharper. So the very definition of the concept is affected by the way we operationalize it. Okay, almost done. What are the implications of all this for fairness? What are the implications of narrowing and sharpening a concept for fairness? I want to say that there's something that we should call maybe definitional fairness. It's a different source of fairness and unfairness than what we tend to talk about with machine learning. Here's an example from a couple of years ago. In the journal Pain, a team of epidemiologists and computer scientists showed that using image processing algorithms, they can successfully distinguish between fibromyalgia patients and healthy subjects by looking at MRI scans of the brain. They hurt their subjects a little bit, and they look at the pain signature that appears in their brain. And this is very different than the kind of medical diagnosis of, say, melanoma, where you already have an established way of diagnosing melanoma. You have biopsy, right? Here, fibromyalgia is just really poorly understood. There are no biomarkers, and there's no reliable understanding of the physiology. Some physicians even doubt that the condition even exists. So the very labels they're using they're unreliable, so to speak, because we just don't understand the disease. They may have very high error rates. What this means is that this image processing algorithm has the potential to do more than simply predict or diagnose. It has the potential to become what is called the gold standard. Right? It has potential to set in motion a coordination process through which neurophysiologists are going to discover new things about fibromyalgia, and the kind of classification will emerge. But notice that this has an important fairness implication. There's a danger that false negatives will lead to denial of treatment. How do we know that when we narrow this concept, important cases that we now tentatively classify as fibromyalgia are just going to be left out? So there are real harms, potential harms to patients who are now receiving treatments or some recognition, and who will potentially not receive those kinds of treatments once the concept is standardized. And this doesn't really fall into the kind of equality of distribution of harms that we talk about with fairness. It's just, I think, a different kind of source of unfairness. So, I don't have a good solution or even a start of a solution for this, but I think the thing to ask is, under what conditions is it justified to use a machine learning algorithm as a measurement standard? What makes a good measurement standard is a big question in philosophy of measurement. And I think this is a great place for philosophy of measurement and data ethics, information ethics, to join forces and ask seriously, because I think we're going to have more and more examples like this, where machine learning algorithms are going to be helpful in detecting and classifying in domains that we don't actually know very well about, don't know very much about. Okay, so to summarize, I've suggested 4 principles for our conversation. They're revisable, but I think I take them as a starting point for discussion about how exactly measurement theory, philosophy of measurement can help think about information ethics. First, my advice is to think of machine learning algorithms as measuring instruments, not necessarily because they are, just because maybe it's helpful to think about them that way, and specifically to see what happens when we think about machine learning algorithms as potential measurement standards. Second, think of fairness as a process, not as a static property. Third, model and predict long-term use cases, not just patterns in the data. And finally, evaluate accuracy relative to ethically and epistemically ideal use cases, not real ones. Thank you very much.
Thanks. I'm going to go over here on the side, old-fashioned style. Thanks a lot, Eran, for that really interesting talk. I'm going to just make some observations about some interesting overlaps between the keynote and Eran's talk. So, in the keynote, we got this picture, which breaks up a machine learning problem into a task, experience, and a performance measure. Okay, and then, so the way I like to think about this, I guess, what is this one? So I think there's different levels at which you can think about this. So I want to think about a range of cases. So the computer scientists tend to operate at what I would call just a formal algorithmic level. And so at this level, you would say something like the task is classification, simpliciter, or something like that, where you're classifying like X versus not X, where that's just an abstract property of some objects in some abstract population that means nothing yet. Okay. And then experience, well, this is just some data relevant to X, not X, of objects in some population, to whether something's X or not. And then performance measure is usually something like accuracy of some sort, and that's, but in again, a very abstract, formal sense, because at this level, none of this means anything. It's just formal. But when you actually apply something like this, so let's think of one case. Suppose X is red marble, and not X is blue marble, and you're trying to sort marbles. Not a very normatively interesting case, but certainly totally applicable, right? And so here you've got observations of marbles. They're colors, I guess. Right. And then here you could just use standard kind of accuracy measures, and that would all seem fine, because there's really nothing at stake here. It's not a normative context. But then you get down to the interesting cases for this conference, where X is something like reoffender, future reoffender, or not. Okay, and then here, well, again, it's data relevant to whatever you think is relevant, so predicting that. And what's normally done is you just bring down the standard kind of accuracy measures. Except then what happens is somebody says, oh wait, but now this is a moral context, so we got to do better in our evaluation of the algorithms. And so what I see in this literature is people trying to pack all the normativity into here. Like, oh no, now we're in a normative context, so we better start thinking about things like bias in our evaluation of the performance of the algorithm. Okay, I think the cool thing about the keynote was it's saying, yeah, no, the whole thing is normative. This whole problem is normative. So the idea that all the normativity that's interesting is somehow going to be packed into just the evaluation of how the thing does, I think is wrong. So I like that. And now here's how that I think ties to Eran. You can tell me if I'm right. Eran's suggestion, he makes many suggestions in the paper. I can't talk about all of them, but I think one of the suggestions that I really like is when we're evaluating, well, not only when we're evaluating, when we're using, because you were talking about using machine learning algorithms, not just for this, but as standards. Okay, I like that. And so that also, on that view, there's something like an ideal use case. And I think really both talks are getting us to try, saying that, and for different reasons maybe, that we should be thinking about these. What's the ideal use case like? And let's build models of that, of this thing, which is inherently a normative thing in the interesting cases. Let's not shy away from that. And then we should be making some kind of comparison between this and this, or maybe these kinds of models will just be used as standards of ideal use, right? So anyway, that's kind of what I observed today and what I thought was interesting in the analogy. Maybe Aaron, you can comment on that. Thanks.
Oh, thanks very much. Hi. My only comment is yes, I agree, and what I'd like to see in this table is this distinction. So the way I would kind of make the table even better is by distinguishing the prediction and the target variable and the direction of the inference. So what I'm trying to say is that if you really want to take ideal use cases seriously, you need to talk about not just the inference from the features to the prediction, but from the prediction back to the variable. So I'm not sure how to add that onto the table, but yes, that's that and the back inference together is a kind of good way to summarize what I'm saying. Thanks a lot.